Hi everyone, I'm very happy to be here today and to make a presentation. And before I start, I would like to say a very warm thank you to the organizers of the conference and also to all participants at the conference. So my name is Gregory. The title of my presentation is Explaining Causation in Global Migration with a Complex System Approach. So in one word, the theme of my research is the causal impact of climate change on international migration. And there, I would like to give you an overview of the data we have on international migration, and especially to illustrate the global increase that we have been observing since the past few decades in international migration. So there you have the growth of global migration around the world from the 70s to today. And you see there a very sharp linear increase in the overall growth of global migration, up to 280 million people around the world counted as migrants. There you also have the increase of the global migrant stock as the world's total population. So you see that now today, more than 3.6% of the world's total population is counted as migrants. And there finally, this last figure, it illustrates again a very sharp increase in the number of refugees around the world since the 1960s. And this also suggests a very dramatic increase in migration crises around the world. So the bottom line here is the following question: why is migration increasing? Someone could say, well, migration is a random phenomenon. It evolves stochastically, such that we just have to let it go. We'll go up and down and up and down, and we just have to cope with crises. Someone else could tell you, well, we have to study causation. We have to know the causes that are behind that increase in global migration around the world. So now, that being said, my research question is the following. What are the strong points of a complex system approach in migration science? And the sub-question, how can we theorize causation in migration with that approach? In one word, I'm interested in seeing to what extent we can make progress in the study of causation using a complex system approach. I will explain the motivation behind that research question. Well, in any case, there's one weakness in causality in the science of migration, and this has to do with some weaknesses of the standard models that migration scientists are using. So there you have two examples of standard models that migration scientists are using. And what I contend here is that they are not sufficient to give us a good grasp of what causation is in the modeling of the process of migration. The first one is a standard frequentist model. It's a Poisson model, and what you have is a conditional probability, and the parameter lambda we are conditionalizing on to obtain a probability distribution is what is called an intensity rate of migration. So what we do is we obtain a given intensity for a certain region for migration, and then we draw, so to say, some conclusion about the probability of seeing some further migration given that parameter lambda, that intensity of migration. The second one, the Markov transition process, is, I have to say, an interesting model. The more I criticize it, the more I'm starting to feel that there's some potential to study migration with that model. What is it? Again, a conditional probability. What we are interested in is modeling migration as a transition process, as a transition from one state to another. What we have there is the probability of obtaining a certain value for a given state y of an agent at the next time step, given a series of transition steps that we've observed before. What that model says is that this probability is equal to the conditional probability of observing, again, that transition to a migration state, of course, at the next time step, xn plus 1, given the state that we are observing before. So what someone could say is that, well, maybe the state of an agent that we are observing now could be used as to draw some causal inferences if we generalize over some kind of statistics. We'll say, the idea would be to say, well, some states might be causally responsible for a transition to a migration state. In any case, that what this model has is a very minimal memory, and we could work that concept of memory to go further in the study of causation, but I contend this is not enough. The problem with causation in global migration is also the following. There is a causal complexity in migration, apart from climate change, as I said before. Various causal factors, political, economic, demographic, as well as extreme events, drive migration. And also, we will be studying that in my presentation. There's a complex causal hierarchy in the phenomenon of migration. Causation operates through a multi-level structure at the agent level, at the micro level, at the community level, at the meso level, or at the aggregate level. Whoops, I should be going this way. Bottom up, whatever, at the macro level. So some scientists will say we have to concentrate on the agent level. Some others will say, no, we have to concentrate on the macro level to really draw some good causal inferences. What I contend here, we need an overview of causation through the old structure, through the old multi-level structure. Here you have a multi-layer causal network that illustrates this multi-scale causal hierarchy in migration processes. You have the micro level, the level of agents, then the meso level, where we have some kind of formation of community clusters, and then at the top, the macro level, of course, we obtain a large-scale overview of global migration trends. On the right-hand side, you have red boxes, and what I contend there is we might have different causal variables that we have to study. The big question is, are there causal loops in that structure? Or is causation top-down or bottom-up? And of course, what evidence do we need to confirm those causal assumptions? And by the way, we will have a big problem when we start to talk about intervention. Why? At which level do we need to do our interventions? At the bottom or at the top? Or at every level? In any case, these are the questions that I'm interested in studying. So what is my proposal? We need to model migration as a complex system in order to describe the links between causal external factors at the boundaries of our system, the agency and mobility of multiple agents at the bottom, and then to what extent these are driving large-scale migration movements. I contend to do that, we need two things. Step one, agent-based models that describe the mobility, interactions, and decisions of agents from which global migration patterns emerge. And step two, a general multi-scale account of causation for complex systems. So through my presentation, I will go through those steps. What's the plan for today? Section one, I tell you what is a complex system approach in migration science. Section two, I go into the first step of my contention, agent-based models. Section three, step two, what should be or how can we theorize causality for complex systems? Finally, I give you a brief overview of the results, limitations, and contribution of my research. So, what is a complex system, first of all? The complex systems are co-evolving multi-layered networks. That's a little bit like as I showed before. There, you can feel that we are dealing with a complex system because we are dealing with a multi-scale phenomenon. And in that multi-scale phenomenon, we have interactions of large number of entities that give rise to qualitatively new kinds of behavior, what we usually call in the literature emergence, like self-organization, memory, and adaptation. Now the question you might be asking yourself, but why should we consider global migration processes as a complex system? Well, Frans Willikens, a very important migration scientist, claims the following: international migration has many features of a complex system. He states that agents drive the system through their interactions without central control, autonomy. Agents adjust their behavior in response to endogenous and exogenous influences, adaptability, and observable systematic patterns are consequence of the behavior of units of the system, emergence. So what I've done there is to show you an overview of the typical features that have been identified in the philosophical literature to be necessary, sufficient and necessary conditions to consider a system as a complex system. These are given in the left-hand side column. Right-hand side column, you have the paper from Frans Willikens, where he explicitly identifies features that are shared, according to him, by migration systems. And those are identified with stars. Those he identified explicitly. And now what I would like to show is that we certainly could identify all those factors in the left-hand side column that are taken to be general features of a complex system in migration systems. So those other features are identified with the daggers. So what is the bottom line here? The bottom line is the following. We have an analogy between a typical complex system and a migration system. So we need to push that analogy further and to see to what extent we can really conceive migration systems as complex systems. But the problem, I repeat, is with causation. How do we conceive causation in those complex systems and complex systems of migration? So what about causation in complex systems? Frans Willikens indicates that complex systems change continuously due to internal forces and external influences such that a system's structure evolves. So he indicates that there must be causation in that system, but other scientists and philosophers have not explained how causation operates in complex systems and, of course, in complex systems of migration. I want to do more research there. I want to know how can we conceive causation in those complex systems of migration. Well, now I move to the second section of my presentation. I want to give you more details about the first step that we need to model migration as a complex system. We need to start from the bottom. We need agent-based models. So, according to Klabunde and Willikens, the aim of agent-based models is to uncover causal mechanisms, right? This is what we need. So, since agent-based models describe a system's behavior as an outcome of actions and interactions of agents, so basically the idea is that what is going on at the bottom level is responsible for the emerging behaviors that we observe at the meso level and at the macro level. Well, we need to start from the bottom. Agent-based models represent the actions, interactions, and mobility between agents. They describe the causal determinants that influence the dynamics between those elements, subsystems, and systems, and they indicate the salient individual drivers like specific life events, age, education, partnership, employment status of migration that are relevant for predictions. So, what are the typical elements of a potential agent-based models that we need? Well, I found some very good indications in a paper written by Tauber. And what we need first is the characteristics of agents and the decisions they make. We also need to define the type of interactions that we have between those agents. they could be exchange of information, they could be cooperation and influence, but it could also be competition. Then, at the meso level, we need to see to what extent there is some kind of formation of community clusters through those interactions, through the exchange of information, through cooperation or influence, and through competition as well. And finally, of course, the feedbacks between environmental factors and general human mobility. So for every agent-based models, we need some kind of underlying theory of decision-making. In the literature, you can find economic underlying theories like neoclassical macro theory, microeconomic expected utility maximization, the theory of new economics, world system theory. There are also socio-psychological theories, theory of planned behavior, for example. And finally, purely empirical theories like where you simply draw inferences from data analysis. Well, now I suggest that we could use a very interesting model developed by Tourna and Hale, and they suggest a model of coevolution that could be certainly useful for migration. The idea is very simple. You have elements that are agents, you have a type of interactions between those agents, and you also have external factors that are determinant for the co-evolution of that system. And what it says is that you will have some kind of feedback loops between agents, interactions, and those environmental factors. And there you will be able to track the evolution of your system. So what we have is what Tourna and Hale suggest is two algorithmic equations, 1 and 2. They are, and what you have there is two dynamic functions, f and g. So what we have in the first equation, we have, what it says is that the left-hand side term will be realized by our function f. What are the specific variables? We have a state of an agent, which is denoted by the little sigma that you see there at time t. And it says that that state of your agent will be realized by your function f. What do you have in the argument? You have a variable lambda, which is a set of environmental parameters. You also have a very interesting matrix of interaction. And the upper index alpha gives you the type of interaction we have between your two agents, in that case, I and J, at time t. And of course, you have to define the state sigma of your other agent. And what you have in the second equation, same idea. Now you will have an update of your matrix of interaction, and now you will have a new type of interaction, which is given by the small beta at a future time step t prime. And again, what you have in your for our function g, the matrix of interaction that we had before, and both states of our agent that we have. So the bottom line is the following. States of our agents are determined by their interactions and the set of environmental parameters that we need to define before. And then you run your algorithm and you can track the evolution of your migration system. This is a proposal. In any case, we can conceive migration as a survival strategy. And the evolution of a system is tracked as a function of state of agents, social interactions, and the environment. It's a different narrative. I find it very interesting, and I would like to push the idea further. So now there are still open questions concerning causation. As I said, we can. The first step is to model migration systems as complex systems, but we need to know what causation is there. That's what I'm interested in. Since agent-based models cannot include all salient causal variables, we still need to inquire where causation is operating elsewhere in our complex multi-scale structure. So these are open questions that we need to ask. Are causes only external, operating from outside at the environmental macro level? Are the decisions, interactions, and flow of information in a community at the meso level the genuine causes of the mobility of every migrant, or are causal chains based on the decisions of agents at the micro level. There's disagreement. If we look at the literature, scientists will disagree on which level we need to consider in our multi-scale structure. And of course, what evidence do we have to answer all those questions? What evidence are we able to gather in order to confirm our causal assumptions? Okay, there's a proposal, very interesting, from Andreas Wagner in a paper written in 1995. It's a good starting point. So, in one word, he addresses directly the question, what is causality in complex systems? And it's a good starting point, according to him. Causation in a complex system can be local or global. That is, causation can be a function of interactions between elements within the system at the micro level, or causation can be a function of the system parameters and exogenous variables at the boundaries of your system. So he shares, so to say, or I share the same intuition about this multi-scale structure. And of course, he indicates that causation can be a function of both levels. What is his definition? For a system S1 with a set omega of individual state variables, X members of that set omega with a potential value X at time t that could represent either a physical quantity or the state of an agent, well, it claims that a causal event will be a change in a state variable xit, and this will be the cause, and the corresponding effect will be a change in your dynamical system, which will be observed through a derivatives, a gradient, or a simple qualitative state transition from alpha to beta in one or more state variables at time t+1. And importantly, changes in state variables cause changes in the subsequent structure and behavior of the system, which will be observed in the system's trajectory. So there's good agreement with, so what I've been saying is kind of agreeing with what Andreas Wagner suggests. In any case, what I have to criticize is the liberality of that definition. Why is it so liberal for a definition of causation? Is because we're studying dynamical systems. Of course, your dynamical system will evolve and you will observe changes in your system. But what he claims there is that as soon as you observe a change, if we take his definition for its words, then every change will count as causally induced, which is too liberal. I mean, because we would like to differentiate between random or purely random changes in the evolution of your dynamical system, and of course, purely induced, changes induced by causal forcings in your dynamical system. In any case, that's a good starting point I would like to contend. And there's a good news. We can update our co-evolutionary model that I just introduced before. I suggest that the model developed by Turna and Eyl allows a causal and predictive interpretation. So now you have the same two algorithmic equations, but they are updated with some kind of predictive taste. Why? We are interested in the future, in the state of a single agent denoted by our variable sigma, but at a future time step. So we would like to predict, and this will be realized by our function f, but then we would like to, so to say, assume that the parameters in our set lambda are causal parameters. So in other words, what we have is the same idea, same algorithmic equations. The left-hand side term will be realized by the right-hand side term. What do we have? The state of our agent denoted by sigma at the future time step t+1. And then we need to consider the past state of that agent and our function f. There we have a set lambda, but now we give a strong causal interpretation and we identify some causal variables, and we believe that those are responsible for the state of our agent. And then again, we have our matrix of interaction between all the agents that we identified ideally in our system. And again, in the equation 4, we will update our matrix of interaction from the type of interaction alpha to a new type of interaction beta, again at the next time step. And we have the same function G. With what we have there, we have the matrix of interactions with the past type of interaction that we had before, and the states of the other agents that we are considering. So, in one word, what we have there is a causal interpretation of the co-evolutionary model that I presented before. Again, we have type of elements, type of interactions, causal variables, and we see to what extent they are feedback together, and we try to track them through some kind of algorithmic tracking. Okay. I'm almost finished with the section 3. I will move to the conclusion. So so 3 more slides, then I move to my conclusion and I will be finished. We still have a problem with multi-scale structures. There's no preferred level at which a causal description of migration system should be furnished. So we have to choose, we have to select salient causal variables and describe the relevant scales and processes that are involved. Thus, our ability to understand causation turns critically on our capacity to represent and explain the interactions and interdependence from multiple levels. So, that being said, we need to study possible causal assumptions that are defended by philosophers. I think it is one important task that we need to do before making those choices, before selecting if we want to choose a specific level, or if we want to consider the whole scale together, then we need some strong causal assumptions that are to be found, that are described by philosophers. So what are those? There are 3 potential candidates. The first one could be reductionism. Multi-scale systems can be explained bottom-up. Sufficient information about the elements of a system suffices to explain the phenomenon at higher scales. So one would say, well, we just have to focus and to gather evidence at the lower level, and the rest will come, according to reductionism. Some other philosophers could defend causal robustness. The behavior of a system is insensitive to changes in its subsystem realizations and fine-grained details. This is very interesting, but because someone would say, someone defending causal robustness would say, well, all levels are, so to say, independent from each other. So multi-scaling might be a trap because, according to causal robustness, there's no feedback between those levels. So we just have, so to say, to study, according to causal robustness, every level individually and then draw some conclusions. And finally, what I believe is most coherent with the position that I've been presenting today, causal dependence or causal bridging. Subsystems are not self-contained. They give rise to emerging simplicity or sophistication through information feedback and coupling. This would be, so to say, my preferred option to theorize causation, to define some causal assumptions, to theorize causation in complex systems, and of course in multi-scale structures. So, in any case, all causal approaches can be pragmatically justified depending on causal factors we isolate and describe. This is why a multi-science approach of causation is needed. This is what I contend. This is my last slide, and then I will move to the introduction, and I will be finished. we get some potential answers from the research that I've been doing. A complex system approach at least would describe how system parameters and exogenous variables causally affect the states of the elements, how changes in the states of some elements causally affect other states, and finally, what are the causal loops between the elements, subsystems, and systems that affect the system's equilibrium. And this would be consistent with what Andreas Wagner is defending in that paper. Okay, now I move to the conclusion, and I would like to present what I believe are two preliminary results of my research. There is an analogy between complex systems and migration systems that supports the objective of theorizing migration with complexity science. We need to push that analogy further. Complex system approach provides tools to represent and explain the causal structure shaping the linkages between humans, the environment, and their mobility. So in one word, I think there's a good analogy between migration systems and complex systems, and a complex system approach indicates paths to make progress in the study of causation in migration science, but also in the foundations of complex systems. Finally, there are also important and crucial limitations to my project. Three central limitations to a complex system approach to causation and to migration science in general. First, what evidence or data can support our complex system models and confirm that migration processes exhibit specific features of a complex system? The analogy looks fine, but we need evidence that indeed migration systems do behave like complex systems as they are defined by researchers. Also, does the intricate structure of our complex system models represent the real migration flows? I've been talking about the coevolutionary model, and to what extent can we confirm that this very detailed structure of our agents, their interactions, the large-scale behavior we might observe in the future do indeed represent what is going on in the world? Finally, can we obtain accurate predictions for migration flows with those models? If you present a model to migration scientists, and of course to policymakers, they will ask you, well, to what extent are you going to make good predictions? I don't know. Now, and this is a strong limitation because, of course, we have, of course, a pragmatic need in using those models is to predict future migration flows. And of course, why we want to do that? Because we want to do good interventions. We want to intervene at the right place at the right time. So finally, I believe my contribution is twofold: to demonstrate the plausibility of a complex system approach to study causality, and to demonstrate that causality can form the methodological core of the interdisciplinary study of global migration. Okay, I will thank you very much again, and I'm looking forward to your comments and questions. Thank you very much.